Good afternoon, everyone. Thank you. Welcome to the post-lunch session of the A.N. Mitra Memorial Lecture and Meeting. And I'd like to take this opportunity to thank the organizers, Professor Alok Mitra and Gargi and other organizers for inviting me for chairing the afternoon session. Without much ado, I'll just go on and introduce Professor Shashank Bhatnagar, who is the next speaker in the afternoon session. He is a professor in the physics department at Chandigarh University, Mohali, India, and his research interests are in mathematical physics, fluid dynamics, and computation physics. Today, he'll be speaking in the memorial meeting on exclusive processes at B factories in framework of Bethe Salpeter equation. And I would request Professor Shashank Bhatnagar to take the floor.
Thank you, Professor Nivedita, and I would like to thank all the organizers for this meeting. It's really an honor and a privilege to give this talk at A.N. Mitra Memorial Meeting. So he was a teacher and a researcher par excellence. He gave me the course Radiation Theory. So that was in the fourth semester of my MSc final, and in the year 1985, and I was really mesmerized by his brilliance in his lectures, and then I was also lucky to be his PhD student during 1985 to 1990, and he was doing pioneering work in the field of Bethe Salpeter equation, and I have learned many things from him, not only academic but also many life lessons I've learned. And so right now I'm going to give a talk on exclusive process at B factories in the framework of Bethe Salpeter equation. And so as we go ahead, I found let me share with you. I'll try to share with you the strong physical intuition that he had, because we worked out a number of things, and we have in the process diversified the framework quite a bit. So I'll just go ahead and so let me go to the next slide. So the outline of my talk is so the first is the introduction about these processes, then Bethe Salpeter equation, then the Charmonium production process. So here I'll talk about these processes that occur that are going on at B factories, that is electron positron colliding to give a virtual photon, and photon then producing a photon and a hadron, and in the process A, the hadron is chi c0, chi c1, eta c, chi c2. Then in the next process you have double Jepside production through two intermediate photons. Next you have the double eta c production through two virtual photons, and then I'll go to the conclusion. So I go to the next slide. Sorry, I'm not able to. Some glitch. Yes. So I start the exclusive process at B factories. So exclusive process, they refer to scattering events, where all the final state particles are observed and identified. So these are the examples of exclusive processes. And and Charmonium production, it's one of the most intriguing subjects and remains one of the most vibrant areas of research in quarkonium physics. These processes, they act like a bridge between perturbative and non-perturbative QCD, because in the sense that you are through virtual photon, a QQ bar pair is being produced. That's a hard process, and followed by hadronization of QQ bar pair into QQ bar hadron, and that's a non-perturbative QCD process over there. And these processes, they provide ideal testing grounds for fundamental theories and also continue to refine our understanding of strong interactions. So if we go through the history of these processes. So you see that these processes were observed by Babar and Belle around the year in the year 2004 and 2005. They they measured the cross sections of these processes to be around 25 femtobarns, and this in fact led to the rapid progress in the theoretical description of charmonium. So So the first calculation of this process was done by Bratton and Lee. So that was in the year 2005 using NRQCD. They got results which were one order of magnitude less than experiment, and it was found that it could be resolved only when they took radiative corrections and relativistic corrections simultaneously. So these two are the famous papers. These three are the famous papers that led to the real progress in this field. Now, additional processes that were observed were at Belle, that is E plus E minus, producing gamma chi c j. So they measured this process at center of mass energies 10.5 to 10.58 and 10.867 GeV. Then these processes were also measured by BESS3 in the year 2021. So this was in the energy range 4 to 4.6 GeV. Then the double gypsy production that produces that proceeds through two intermediate photons. They were also measured. They were also measured at Belle in the energy range 10.6 GeV, but they could not see clear signal in their measurements. Then theoretical models that were proposed to describe this process was NRQCD, light cone expansion, vector dominance model, and the Bethe Salpeter equation model. So NRQCD factorization, if you see this, you see that the cross section, it can be factorized into the short distance part, that is Cn, and the long range matrix elements, that is O and H. So these short distance short distance these coefficients Cn are calculated perturbatively in the strong coupling constant alpha s, and these long range matrix elements, they are the non-perturbative part. So we'll go to the Bethe Salpeter framework now. Sorry, I'm having problem in going to the next slide. Yes. Now the motivation for using Bethe Salpeter equation is it's a dynamical equation based approach, and it incorporates relativistic effects non-perturbatively. So this is even at the lowest order in QCD. Now the relativistic effects of quartz spins, they are incorporated through the BS wave function, and the BSE framework is applicable to a number of processes across different energy scales. So these are the processes we studied in lowest order. So what we see is that the lowest order QCD expansion in alpha is sufficient because the dominant contribution, it comes from the lowest order diagram in BSE, and the higher order alpha and alpha EM corrections, they are expected to be negligible, and right now they are ignored. So I'll go to the next slide. I'm having actually problems in shifting the slide. Yes. So there's the form of the Bethe Salpeter equation. So it describes the bound states and QFT. So the Bethe Salpeter wave function is psi, k is the interaction kernel, and SFs are the propagators. So what we do is the reduction from 4D to 3D form using the covariant instantaneous ansatz, where you split the hadronic internal momentum of the hadron into transverse part and longitudinal part. Now the longitudinal part is sigma p mu. It's longitudinal to p mu, and the transverse part is q mu hat. That is transverse to to the hadron momentum P, and the 4D volume element is D4Q is D cube Q hat MD sigma. Now this the first paper that dealt with this was with Professor Mitra in the year 1992. It was done, but then the utility of this framework is so much that it is being applied even now, that BSc under the covariant instantaneous approximation, it is being used by the GL1 group as well as the JKE group, and they are continuing to use it as shown by these publications. And the important thing over here is, now why people are so attractive to this framework, because Q hat square is a Lorentz invariant quantity. Now the Lorentz invariance of Q hat square leads to invariance of transition amplitudes, 3D forms of transition amplitudes, as well as the 3D forms of Salpeter equations. That is the most important aspect of this. So I go to the next slide. So the properties of Q hat square, so it enhances applicability of BSc under CIE across wide range of energy scales, ensures the Lorentz covariance of 3D forms, and we have used the one gluon exchange vector type interaction kernel. We land up at the 3D Salpeter equations. There are four equations in number. The last two equations are the equations, they act like the equations of constraint. So we are going to just tell you what we actually do, and so we split the wave function into plus minus and plus minus components. So first we worked out the mass spectral calculation. So we start with the full 4D PS wave function that was proposed by CHL Smith in the year 1969. It's a famous paper, and so you see that the pseudo-scalar Meson wave function can be written as a superposition of the various Dirac structures. That is a unit operator over here. P slash Q is the internal moment of the hadron, and this term. So these phi's are the Lorentz invariant structures because they depend upon Q square, Q dot P, and P square. So in the earlier works, now you see in this, when you use this wave function for calculation of various meson observables, we see that all the Dirac structures do not contribute equally in any calculation. What we saw is some Dirac structures contribute more than the other Dirac structures. So what we did was we devised the power counting rule to distinguish the leading Dirac structures from the sub-leading Dirac structures. So these are the papers where this thing is published, and we calculate the electronic decay constants. We found that the maximum contribution, it comes from the phi1 term, phi1 amplitude, then then the next contribution, it comes from the P slash term, then Q slash and P slash Q slash. These are the subleading Dirac structures. They contribute around 20%. This contributes this, and these two, they contribute maximum. And amongst these two structures, phi1 contributes most. So this is the most dominant structure in the case of pseudoscalar meson. So these are the leading amplitudes. So I go to the next slide now. So what we did, 3D, so these 3D Salpeter equations, they are the coupled equations. So we tried to decouple them. We found that they decouple in the heavy quark limit. We got the mass spectrum and plus analytic forms of radial wave functions. The radial wave functions were used to calculate the various transition amplitudes. And the transition amplitudes, we applied them were to leptonic decays and the radiative M1 E1 decays, and now we are applying the same to production process. Now I just go to this topic. We measured the cross section. We calculated the cross section for the process E minus E plus going to gamma chi C0. So you have E minus and E plus, and I let to give you a virtual photon. Again, that creates quark anti-quark pair. And so a photon and a chi C0 meson is produced. So this is the direct process. This is the exchange process. exchange process, it results by interchanging the, I'm sorry, by changing the direction of the quark loop. So in that case, MFI is this. You can express MFI in this form. So there's the leptonic leptonic part of MFI. So there's leptonic current and there's the hadronic part, hadronic current. So you see that the hadronic current is nothing but the transition matrix element for electromagnetic current for the transition gamma star to gamma chi c 0. So again, we use the full Dirac structure. We write down MFI for this case, again in terms of plus plus and minus minus coefficients. We worked out the quark propagators in the complex sigma plane over here. Then we saw that you can express mu. Mu is the hadronic part, hadronic tensor in terms of three form factors: beta 1, beta 2, beta 3. But gauge invariance demands that k mu mu equal to 0, and so beta 2 becomes equal to 0. So you see that you have only two independent form factors, beta 1 and beta 3. They act like the coupling. They act like the effective coupling of the bound states with the virtual photon, and these are the radial wave functions we worked out using the mass spectrum. And this work is these radial wave functions have been published in this. So over here, the interesting part, you see, the reason for taking the entire Dirac structure is the Dirac structure of the wave function, Bethe Salpeter wave function, is the following: that you have the terms like gamma dot q hat by m. So they are like the gamma dot v terms in non-relativistic QCD. So gamma dot q by m, they reflect of the order of v corrections to MFI, right? Over here. So they are consistent with NRQCD power counting. So you see that the covariant structure, full covariant structure of BS wave function automatically generates expansion in powers of quark relative velocity in NRQCD. So in NRQCD, you see that the um, lowest order contribution, it does not involve relativistic corrections. But over here, if you are evaluating the lowest order diagrams using BSC, you automatically incorporate relativistic corrections in your theory. And there's evident from the fact that the calculations of cross sections that you do using the leading order or the lowest order diagrams, right? They the result that you get is quite substantial, right? Unlike the case of NRQCD, where the result was one order of magnitude less than the experiment. So there's the reason for taking the full Dirac structure. Now over here, the problem over here we found was we drew the plots of the form factors beta 1 and beta 3. So they are two-dimensional functions. We plotted versus q hat and root of s. So we found some discontinuities in these plots. So right now we have ignored these discontinuities, and you see that they are very narrow regions of discontinuities. And discontinuities become narrower with increase in root s. We are plotting root s along this axis and q along this axis, and the integrands of the form factors along the vertical axis. So these are the regions of integration, and then I go to the next part. So the cross section is expressed in this form in terms of beta 1 square and beta 3 square. Beta 1 and beta 3 are the form factors. Then we worked out the cross sections. So we see that at 10.6 GeV, our cross section is 3.810 FB, femtobarns. Now, other models, for example, Chung in the year 2021, their cross section is 3.11. The central value is this, and then similarly, the other one is 1.885, right? So it is still, so you see that sigma is within the upper limits of both Pelle and BES3 for chi-0 production process. Now I go to then we studied the variation of the cross section. We tried to analyze the just a second. We also plotted this cross section over here. We found some fluctuations in the 4 to 6 GeV region, but you see, when you go to high energy, it shows a power scaling behavior, power law behavior. This is very important. Now So we analyze the cross section in terms of these form factors beta 1 and beta 3. These are the plots of the form factors, and we have done the detailed analysis of this. Anyone is interested, they can have a look at our paper. And then we went to the study of this process, that is E plus E minus going to gamma chi C1. And over here we again found out the gauge invariant form of MFI. So again we see two form factors over here. Then so these are the analytic forms of the radial parts of wave functions. And there's the full 3D structure of the wave function, Dirac structure of the wave function. Then again, we worked out the cross-sectional formula. That is, we worked out the cross-section values. So you see that at 10.6 GeV, the cross-section that we have is within 1.2 sigma of the Belle measurements. So 11 is the Belle measurement, and I'm sorry, yes, 11 is the Belle measurement. I did not list. Yes, over here, Eblikin et al. Eblikin et al. So there's 11 is, I'm sorry, it is best 3, and 16 is the Belle. So this is actually, in fact, the 16, it is in fact the Belle result. And 4.6 and 4 GeV, it is the best 3 result over here. Now, so we see that at 10.6 GeV, our result is within 1.2 sigma of the Belle measurement. At 4.6 GeV, 4 to 6 GeV, we see that it is within 2 sigma of the best 3, and at 4 GeV, 2.8 sigma. So you see that when you study this process at low energy, that is the 4 to 6 GeV, the importance of insertion of higher order QCD effects becomes more and more important. Whereas at 10.6 GeV, you can explain number of things using the lowest order diagrams. So now I go to the third process, that is eta C production. So these are the results of this process, and again we analyze it using the form factors. Then I go to the next process, that is E plus E minus going to two photons and producing two vector mesons. So this process proceeds through. This process is quite interesting. It proceeds through two types of diagrams. So there's the photon fragmentation diagram, where the virtual photon fragments into fragments into QQ bar pair. QQ bar pair hydrogenizes into J psi, and and the other process, the quark rearrangement process, where each virtual photon splits into quark antiquark pair. But one of the quarks, for example, this hadron receives quarks from the first photon as well as the quarks from the second photon. So there is a rearrangement of these quarks. So therefore, we call it the quark rearrangement diagram, and it was first studied by Bodwin, Bratton, and Lee. So this was the first work they did in the using NRQCD. So this process we worked out using the Bethe Salpeter equation framework. So you see that J psi and J psi cross section is suppressed by alpha square alpha square compared to J psi and eta c. That was the first calculation that was done in the double charbonium production process. However, you see that the fragmentation diagrams are enhanced by S square by 16 m raised to power 4 compared to rearrangement diagrams. So this leads to the cross section of sigma J psi plus J psi production to be greater than the cross section for J psi plus eta c production. So I go to the next slide. So I'll skip this slide. If anyone is interested, you can just go through our. What is this? I'm not able to go to the next slide. I'm sorry. Oh. Please forgive me. Yes. So these are the amplitudes for the fragmentation diagram and the exchange diagram. And then I go to the next slide. And so here we worked out the cross sections. We worked out these integrals G1, G1 prime, G2, G2 prime. So you see that these integrals, they're in turn related to leptonic decay widths, and you see that G is always greater than G prime. Because G for the case of gypsy is always greater than the sorry G and G prime. They are their values are such that FV for gypsy meson always exceeds FV for Psi2S meson. The relationship between G1 and G2 and FVs are these. So again, I go to the next slide.
We have about 2 minutes, 3 minutes.
Yeah. So let me try to wind up. So there's the eta C production process. So here only the quark rearrangement diagram, it plays a role, and these are the results. Then the conclusion, we studied the production process at B factories at 10.6 GeV for this process in the framework of Bethe Salpeter equation and covariant instantaneous ansatz. And the form factors we worked out, substantial contribution from the lowest order diagram is seen. Cross sections have been analyzed in terms of form factors. We also calculated the percentage contribution from the fragmentation and rearrangement diagrams along with the interference of these amplitudes in the calculation of the cross section. So this talk was based on the talk I gave a fortnight back at 21st International Conference on Hadron Spectroscopy and Structure. That is Hadron 2025 at Osaka University, Japan, in during March 27 to 31 this year. And these are the two papers on which this work is based on. So thank you very much.
Thank you very much, Professor Shashank Bhatnagar, for a very illuminating talk on the Bethe Salpeter equation. When I was a student in the master's and was taught by Professor Mitra, he was at that time also doing the Salpeter equations. Yeah. So I thank you for that. Very.
He was a luminary.
Yeah. He's been talking about it for quite a while. But when I came there, also he was working on it. So that was nice to hear. And so we have a few couple of minutes for questions. So any questions for Professor Bhatnagar? So let us give a very big hand to Professor Bhatnagar for a very wonderful talk. If there are no questions, I enjoyed myself very much. And go on to the next speaker.